In this media, we are going to learn how stabilizers are used to reduce a ship's roll. Assume you're on a ship in calm seas. The ship's stability is based on her center of gravity, CG, and center of buoyancy, CB. The ship will remain upright and stable as long as the CG and the CB are lined up properly. Smaller waves do not have much impact on a large ship, but as the wave size grows larger, there will be a corresponding increase in the wavelength, and you'll start to notice the ship's roll. The ship will roll from side to side, following the waves. This is due to the fact that as the wave swells on one side of the ship rises, the ship creates greater buoyancy on that side, resulting in a force that causes her to lean over. Most of the time, a ship will ride the waves, softly rolling from side to side. Sometimes, when the wave period is the same as the ship's rolling period, we have what is called synchronous rolling. This results in the ship's roll angles rapidly increasing and may even lead to the capsizing of the vessel. Apart from that, slight rolling is not an issue on these ships, and you'd expect a cup of tea or water to stay on a table when you are on a ship. Stabilizers are used on ships to reduce rolling. A stabilizer's purpose is to counteract the force of a wave. When the crest of the wave hits one side of the ship, the tipping force is at its peak. As the wave crest passes over the ship's center line, the force nearly vanishes, and as it passes to the other side, the force increases, but in the other direction. All of this must be balanced by the stabilizer. It must be able to adjust the amount of force it generates based on the exact location of the wave. There are two types of stabilizers, active and passive. Bilge keels are an example of passive stabilizer. These are protrusion on hull's bilges. As they move up and down along with the ship, they produce turbulence. Due to rolling, the bilge keel produces thrust which reduces rolling. The thrust generated by the bilge keel is small and constant since they are passive. Both keels will do effective dampening of the roll, and they can be easily installed. Hence, they're a common design feature on many ships. Passive anti-roll tanks are another technique used for stability. These are the tanks that are placed at the ship's widest points. When the ship is upright, the amount of fluid on each side will be equal. As shown in the animation, that as the ship sways, fluid on the lower side will rise and fluid on the higher side will decrease. If one can control the flow of fluid, one can have most of the weight in the lower side as the wave rolls over the ship. One can counter the roll by keeping the fluid in place while the wave crests, and then releasing it at the correct moment to allow it to flow to the other side in time to counter the next wave as it arrives. By adding other controls, one can make them semi-active or even fully active by adding a gyroscopic stabilization system that pumps water across whenever needed. As the pumping of water to the other side is time-consuming, you won't be able to accomplish immediate stabilization. The fin stabilizer is our only option in that case. This is the most prevalent type of stabilization aboard cruise ships. The fin stabilizer technology comprises of a hydraulically driven underwater wing. It resembles the bilge keels. The key difference is that you will be able to modify the angle of attack with these active and dynamic fins. If you look at the side profile of a fin, you can see what happens when it rotates. If you turn it one way, the water flow produces a massive force in one direction. You can instantaneously switch the direction of that force by turning it the other way. With proper gyroscopic control, all you have to do now is to rotate the fin to counteract the wave's attempt to roll the ship. You can even utilize it to counteract a roll caused by external forces such as wind or the internal movement of people or cargo. However, the biggest disadvantage of these fins is that they will only work if the ship is moving. They require a flow of water across them, but below a particular speed, typically around 6 knots. That flow is insufficient to create a significant righting force. Fortunately, most cruise ships have a minimum speed that is considerably beyond this, so it is not an issue during voyage. So, in the case of cargo ships that usually travel at slower speeds, active fin stabilization is not installed. However, there are container ships that have active fin stabilizers, but only if their average cruising speeds are high enough to maximize the benefit.
Ships roll during heavy weather. Stabilizing tanks on ships reduce rolling. Ships roll during heavy weather. Stabilizing tanks on ships reduce rolling. Ships fitted with passive tanks transfer water between two wing tanks via a duct fitted with baffles. As the ship rolls, water initially moves from one wing tank to another through the duct in the direction of the roll. When the ship returns from its maximum angle of roll, the baffles hold the water in the wing tanks. Even when the ship returns to its original position, water, for some time, still moves in the previous direction of the roll. This causes a moment which reduces the momentum of the ship and the rolling period. In a controlled passive tank, the valves control the transverse movement of water. The valves restrict the flow of water or air in this fully enclosed system. In ships fitted with active controlled tanks, water is driven from one side to the other by an impeller and a series of valves. The impeller controls the amount of water, and the valves direct the flow of water in opposition to the roll. Here, the required quantity of water is quickly pumped in the opposite direction of the roll.